This screencast is focused on PID control, starting out with the ideal formulation and then deriving the real versions that are used in practice. The motivation for the integral term is to remove offset that occurs when you have a proportional only control, and the motivation for the derivative term is to have better disturbance rejection. In the equation below, you see that the controller output, which is the manipulated input u as a function of time, is equal to several different terms, including the bias term, u naught, a proportional gain term, kc, which multiplies the error, a term involving the integral gain, which multiplies the integral of the error with respect to time, and then finally a derivative gain term, which multiplies the derivative of the error with respect to time. Now, very often you'll see this written without the bias term because over time we can really think of this bias as being absorbed into the integral action. This form with the proportional gain, integral gain, and derivative gain is written differently on the next slide. Here, the second form is what we more commonly use in process control or chemical process systems. And there you can see that the proportional gain really multiplies several different terms. So Kc still remains the proportional gain term, but you see now that inside the brackets we have this integral time. Tau sub I is a tuning parameter, so 1 over the integral time multiplies the error, the integral of the error with respect to time. And then finally we have a derivative time tuning parameter. Now these are directly related to the previous notions of integral gains and derivative gains in the following fashion, where you see that the integral gain is just the proportional gain divided by the integral time, and the derivative gain is just the proportional gain times the derivative time. Now we can write this in the Laplace domain in the following fashion. So u of s is simply kc times 1 plus 1 over tau I s plus tau ds all times e of s. So now we can think of this as the controller transfer function g sub c of s. And we usually see this written using the notion of a common denominator. So let's rewrite that as the numerator is tau I, tau d, s squared plus tau I s plus 1, all divided by tau I s. So we can think of this as the ideal PID controller transfer function, and similarly up above we've written the form of the ideal PID in the time domain. Now the derivative term cannot be perfectly implemented, and really you can see this from the bottom. The transfer function representation has a higher order numerator than denominator, so that could not be perfectly implemented in practice. In order to be able to implement the PID controller, we first need to use the notion of a filtered error signal, which is shown as the first equation. In the Laplace domain, that's represented in the following fashion. So our signal E of f is a function of the Laplace domain variable. S is simply tau fs plus 1 times E of s. Now we can take the Laplace transform of all the elements in the second equation to find the following. And we can make the substitution for the EF of S term into that third part of the equation. So then we can rewrite the expression as follows, which this then gives us a transfer function that's relating the error signal E of S to the manipulated input. So we can think of that as being the controller transfer function. In practice, for analysis, we'd like to rewrite that with a common denominator so that we have a single numerator polynomial divided by a single denominator polynomial. So going through a couple of algebraic steps here, U of S is KC. So let's go ahead and write the first two terms, which gives us what we recognize as the proportional integral action. And then this final term, which is the filtered derivative action. So again, forming a common denominator, we find the following expression below, and we can further expand on this to find the following. Where again we note that now for this real form of a PID controller, we have a second order polynomial in S divided by a second order denominator in S. In practice, this is used for analysis when you do root stability analysis and that sort of thing, because it's perfectly fine to implement this in the time domain form shown earlier. Now, we may not want to work with the derivative of the error signal, particularly if we're making set point changes and step set point changes, which would make it hard to differentiate the error signal since it's going to change in a stepwise fashion. So what we're showing with this set of equations is we're rewriting this error term in the derivative part of the PID expression and making it clear that that's the set point minus the output. So then if we decide that we don't want to differentiate the set point because we may be making a number of step changes and just want to operate with the measured output, it makes it clear then that in this final part of the PID expression, what we'd want to have is a minus tau d dy dt, where we're taking the derivative of the output rather than the error. So this is the derivative of the measured output y. And we have similar problems in that you can't perfectly take a derivative, so we'd really like to use a filtered measured output before we take the derivative of the output, and that's going to be shown on the next slide. Here we have a first order filter that's being applied to the measured output in the first equation. So again, that's represented in the Laplace domain as the following transfer function. YF of S, where this is now the filtered output, is the filter time constant tau sub f s plus 1 times the measured output in the Laplace domain y of s. So similar to what we did with the expression involving the error signal, we get something similar now when we're working with the derivative of the output. Okay, so now we have the minus tau ds over tau fs plus 1 times the output signal y of s, which we might want to write in the following fashion. So we can think of this as being a real PID equation where the derivative is taken of the measured output rather than the error. So we can think of this as being the PID y, if we want to think of that as being filtered, we might want to use that expression, just to note that it's a PID, but the derivative is being taken now of the measured output. In this final slide, we see additional parameters. So what we've done is we've captured this filter time constant as some value alpha times the derivative time, and alpha is usually around 0.1 to sometimes as low as 0.01. So somewhere in that range. I often use about 0.1. You'll also note that we have now a set point weighting factor beta, and then we also have a gamma term shown here. So you'll see this as part of the 2 degree of freedom expression when you use that function in Simulink. The purpose of the beta factor is to minimize what we call kind of the bump that you get when you make a set point change, the proportional kick. And the gamma term is very often set equal to 0, so that we're only taking a derivative of the measured output. So beta is often reduced to reduce the proportional kick. Gamma is often set equal to 0 to make certain that we're just taking the derivative of the measured output y. So again, beta is often less than 1 to reduce the effect of the proportional kick, and gamma is often equal to 0, so that we're taking the derivative of the measured output rather than the error signal. And that often gives, you still want derivative action in order to have good disturbance rejection. To summarize, then, we've developed the top expression in the Laplace domain for real PID, where again we're taking the derivative of a filtered error signal. And the second expression is what we use for a real PID, where we're taking the derivative of a filtered output signal. Hence I call that PID Y versus the top one a real PID E.